Welcome to solverfy.
We're told a vertical trapezoidal gate that is used as an automatic valve is held shut by two springs attached to hinges located along the edge AB. Knowing that each spring exerts a couple of magnitude 1,470 Newton meters, determine the depth of water for which the gate will open. Okay, so I've reproduced the drawing here a little bit. So here's our valve gate, and there's some springs up here holding it shut. Obviously there's a wall here, and then there is water behind that wall, and if it gets deep enough and if the pressure gets great enough, then this the force of the pressure will overcome the force in the springs, and the gate will open and will let water out. So we need to figure out a few things. We know that the depth, so we're looking for the depth of the water that will give this, that will open this. We know how far from the bottom of the gate is. We know these dimensions, the widths, and we know the height of the gate. So the area, I'm going to break it into three pieces, two triangles and a rectangle. You could do it in terms of two triangles here and here too, but I thought it's easier for this. So the area of this region is B2 times H, and the area of one of these regions is 1/2 H times B1 minus B2 over 2. So this distance here is this value. Now we can find the centroid, and I've measured y down from the level of the water and x from the center of the gate. So A times the centroid of the trapezoid is the area of the square times the centroid of the square plus 2 times the area of this triangle times the centroid of this triangle, because we got two of them here. Now we can figure out what y1 and y2 are in terms of the dimensions we were given. So we know that the centroid of the square is right at the center of the square. So we need to go down a distance d, back up a distance a, and then back up a distance h over 2, and that will locate the centroid of the square. Likewise, the centroid of each of these triangles, we have to go down d, up a, and then up 2/3 of h to locate the centroid of each of the triangles. We can plug everything in, and we wind up getting that y bar equals 0.55 plus d. So let's see here. Yeah, so about 0.55 up from here. Okay, so somewhere in this region here. Now we can, again, if we calculate the area, which we had to do to get this anyway, and then we can calculate area moments about the x1 axis. So this is about the x-axis. So this is the x-axis here. And for the square, its centroidal area moment is this value. And then we have the area of the square times the distance from this x, from the surface of the water to the centroid of the square squared. And likewise for the triangles. We have the centroidal area moment about the centroidal x-axis is this, and then the area of the triangle is here, and then the distance from the surface, the water, top of the water to the centroid of the triangle is this distance, and we square it. we can then get the total area moment about this axis for this trapezoid is this plus 2 times this. And if we do that, we can plug in all the numbers. We have everything in terms of d. So if we plug all that in, we get this expression here, 0.170 minus 0.572 times d plus 0.5202 times d squared. And then we know the center of pressure is the area moment about the x-axis, the area of the gate, then times the centroid, the distance to the centroid of the gate. And we know that we can we have all these things in terms of d. So we find that the center of pressure is 0.3264 minus 1.1 d plus d squared, all over minus 0.55 plus d. Right? So we have this expression now in terms of d, and now we need to do some mechanics to see a free body diagram of the gate. So the gate is pivoted about this point, and there's a couple springs holding it shut with moments, and then we have the resultant force from the pressure in the water acting at some distance L from this pivot point. Now we can figure out that if we go back and look at this picture here, we see that D equals, let's see here, so the center of pressure, so the center of pressure is at D minus A minus H plus L. Okay, so that's D minus A minus H plus L. So, in here. So that's, we get the center of pressure in terms of D. And so then in terms of the center of pressure, I said in terms of L. Right? So that's what we have in this. And so we know L equals A plus H plus the center of pressure minus D. Right? So now we got L in terms of D. Now, for this thing to be in equilibrium, to stay shut, we need that this the resultant force here has to be less than 2 times the moment. So at the critical angle, the critical value of the critical depth, this will be an equality. 2 times the moment is 2,940. And then we know the resultant force from the pressure is the density of water times G, which is this value, times the area of the trap door, or the gate, and times the center of pressure. Now we have everything we need. All right, so we have this. We can plug that into here. We can plug this into here. We have that in terms of D. We can plug this into here, and we have that in terms of D. And so we get a function of D over here equals this, and then we can solve for D, and we get that D equals 2.86 meters. Right? So again, this is a function of D here. This, here we have a function of D from here. And so this is a function of D, and it equals some constant, and so then we can just solve for D. And I didn't go through all the algebra because it's kind of long and tedious, but you should be able to do that by now and get this answer.